Alright guys, in this video I'll introduce you to the concept of piecewise approximation. So up until this point we've been only approximating functions and or solving differential equations using one element, and that's not really the point of doing this, because well, the error we make is very big, and the solution becomes very coarse. So before really showing you in the next lecture how this is done, how you solve differential equations using a systematic approach, I want you to really see this using the simple concept of approximating a function before we're moving on to actually solving differential equations, because the knowledge gap tends to be quite high. So this video will be quite lengthy, and I will show you all the details you need to know to really solve this, and I'll draw parallels to doing this by hand, but you will see that this method really is extensible in for very large problems, many elements really, and you will see that the same technology will be applicable to solving differential equations. So we will visit our example equation here, the sinusoid, and we will approximate it using piecewise linear functions. And as an exercise, you will be solving this in a work package for a different kind of equation or a function, and also using quadratic approximations. So you will figure out how to do that yourself by, well, maybe watching the next video even before actually diving into that problem. So let's start. So we left off by just solving, approximating this red function here, this one here, UE, using one approximation in the whole region. So let's go back and see how this problem is solved using one linear approximation. So we have our function here, UE. I'll just copy paste stuff, and of course this is x, so we need the symbolic variable x in order to be able to do this. And now in order to do this, we need, of course, our basis functions. So I'll insert this here. So this is the general form of the basis functions. So now if I add a and b, which is our of range for this, then we get our basis functions in this way. And now we can also evaluate our basis function, our general basis function, into our basis function for our current region, which is this capital phi evaluated at between 0 and 1. So then we get back what we recognize from earlier here. So phi is evaluating this thing at a is equal to 0 and b is equal to 1. Good. We use this form because, well, for each subregion we will actually be needing to reevaluate this thing for each subregion, and we will get to that later. For now, let's plot this this function, this true function, this true solution. Right, so we get this thing here. Let's actually keep this color scheme to red for a true function or true solution, and blue for the approximation. Good. Now we need to define our unknowns. So a linear approximation, a linear function, is of course approximated using two coefficients, or in this case it is our nodal values. So these are unknown nodal values, the endpoints of a line, and our approximation thus becomes capital U is just phi1 times U1 plus phi2 times U2, and I'll write it this way just now because for clarity's sake. Then we have our residual, which we formulate like so. So this is the difference between the approximation and the exact solution. And we formulate our equation, our Galerkin approach here. So we are integrating r times phi1 with respect to x from, well, our range, which is the whole range, 0 to 1. And we're just creating the list, so we're doing this for phi1 and for phi2. Okay, so our final equation thus has two unknowns, u1 and u2, and we have two equations, and we can solve this using the solve function analytically or symbolically in MATLAB to get our two coefficients. Now, these guys don't tell us anything because we want to really evaluate this somehow visually. So first we create our approximation by just substituting capital U. So we're changing our capital U to these U1 and U2 values. So substituting, we're simplifying, and we're throwing VPA at it just to get some numbers and get rid of the irrational number here, pi, and get some easy to read thing here. So obviously this is a first order polynomial, and we can plot this now. So we're plotting here, and then we're gonna do hold on to be able to plot another thing on top, and we'll set this to blue. And we're plotting the same region. So here, so this thing is of course minimizing the residual. So this area here is of course the minimum area which we can get when we are just moving the endpoints around. All right, so this hopefully you know since earlier. Now, what I'm proposing is to, okay, let's split up this field. So let's go from 0 to 0.5. Do the whole thing again, just from 0 to 0.5. Okay, so I'm gonna split this into a second cell here, and I'm gonna do the whole thing once again. So first I'm plotting. I'm gonna plot the true solution here. I'm putting figure here, so that means I'm creating a new figure, which means it's gonna plot a new window, if you so will. So that's gonna just create another one here for me. And now I'm going to do I'm going to re-declare out my symbolic values here, x, u1, and u2, and I'm gonna change my range. So I'm gonna go from x1, I'm gonna say x1 is 0 and x2 is 0.5 instead of 1. So I'm just halving the domain. All right. So my basis function is of course going to change. So I'm using the capital phi here, which is my general basis function. It's valid for any a and b. And I'm just redeclaring the lowercase phi here to just be between 0 and 0.5. So this is it here. And you can go ahead as an exercise and just evaluate this guy now in 0 and 0.5 just to see that it makes sense. All right, and then I'm just copying things. So I'm just gonna go grab this guy here, and I'm gonna copy it in here. But actually I'm gonna do it quite a little bit different here because I want to show you an alternative thing. So instead of going ahead and do well, phi1 times u1, I'm just going to do a matrix multiplication. Because this is a row vector and this is a column vector, this thing here will yield the same operation as this thing. And I hope you understand this. Otherwise, you have to go back and just do basic linear algebra to see that this is true. Because we're going to use a lot of linear algebra, I suggest you get very comfortable with it. Okay, so we have our approximation now for the range 0 to 0.5. Now we formulate our residual the same way we've done before. So we have our residual here, good. And now I'm just gonna create the equation, and I'm gonna create the equation in a similar way. So what I'm gonna do is basically I'm gonna do this. I'm gonna do r times phi. And yeah, so let's run that. So it's gonna multiply r with my two basis functions. And in order to see this, because this phi, remember, is a row vector, we cannot see it. So I'm just going to transpose this. So now I can see that this is actually a vector, and I have r multiplying phi1 up here in this first element, and r multiplying phi2 in the second element. Okay, now I can formulate my equation. So I can say, okay, the equation is going to be this, but integrated. So I'm going to integrate both of these because this is a vector, right? And with respect to x from x1 to x2. And I'm going to set this thing to 0. So both of them will be set to 0 by doing this. So I get an equation system, and I have two unknowns and two equations. So that means this problem is solvable. So I'm just going to copy paste stuff again from earlier in here, and I solve this thing. Of course, there's a bunch of irrational numbers there, so I'm going to simplify and put VPA on that. So now I'm formulating my approximation here. So this is my approximation for this range. Again, I'm going to plot to make sure that you all see what I'm doing here. So now this is what I have. So what I've essentially done is I'm saying, like, all right, give me the best approximation in this range 0 to 0.5, and I get this line here. So that's the best approximation for this function in this region. Okay, now let's say I want to do the same thing but for a different region. So that means I'm going to copy this thing here down here. I'm just going to change this. So I'm going from 0.5 to 1. So I'm doing the rest of the region. I'm going this way here. And I'm going to show you that this thing will actually create a line down here, and we'll get a jump here. Yeah, but I'm getting ahead of myself again. So let's just do this. Yeah, so the region has changed and everything is basically the same. So I'm just going to copy all of this stuff and put it down here, like so. And I'm see here, like x1 is of course dependent on this stuff. So yeah, everything is going to fall out nicely if I just run this. So now I have done two approximations. I've approximated this first half and this other half. But see that there's something going on here. There's this discrepancy. These both points are in the same x value. They are 0.5, but they have different u values because I'm doing this separately, and that's a bad model, let's say, because I get this solution jump. I get this jump in solution, and that's quite bad. You cannot work with this. You have like this arbitrary thing here, like which one of these solutions will you use? Is it this, is it this, or is it half of it? Is it the middle point here? Like which one is it? And how do you connect them? If it's the middle point, then of course this thing will go down there. So I'm not really taking into account that this should be a continuous function. And this is a bad approach. You cannot do it this way. It's like it's one approach, but it's not very good. So on average, if I take the whole region into account, this is not the best solution. So if I look at my area, how big of a difference or how big error in terms of area I'm doing, this is quite bad. So what other approach can I take here? Well, we need to do a little bit math. So let's take a look at it. So I'm just gonna create a new section, and I'm gonna copy and paste in approximations, stuff you have seen already. So my approximation is the following. So I'm changing the index to j here for a reason which will become apparent soon. So u of x, my approximation, is of course the sum of all the basis functions multiplying all of my coefficients. Then Galerkin states that, alright, over the region, and omega denotes the region here, I'm taking the difference of my approximation and true solution, and I'm multiplying that by a number of basis functions, and I'm integrating, and I'm setting this to 0, and then I'm fine. So this is going to create my equation system, because I will get several of these depending on how many basis functions I have. Okay, so now what we do is we insert the approximation into the Galerkin method. So we insert u, capital U here, into our approximation, and we get the following. Summation is thrown in here, and I call phi I here. I'm putting that outside, and I call it different. So I'm sort of summing over the j values. That's sort of missing here, but I'm just gonna write it in here. So I'm summing the j indices, and all of these are then multiplied by my basis functions out here. So what I can do now is I can expand this. That means I can multiply this phi I into both of these terms, and I get two integrals if I separate them. So I have the summation still in here. So I'm taking phi j multiplying uj and phi I. So this phi I has been multiplied in here. So I'm still summing over the j here, but I'm gonna be very careful about this because I'm soon gonna break out uj out of this and put it outside. Okay, and this minus sign is so I'm separating these two integrals. I'm having this minus sign here. That's this minus sign, and then I have on the other side on this in the second term I have of course ue multiplying phi I there, and this is set to 0. Right, now what I'm doing now, so I'm gonna move ui out of there, of this expression, and I can do that. That's a valid operation. So I'm gonna move ui out of this expression, and now this thing becomes, this is like this is an index notation, but this sort of makes more sense if I write this as a matrix formulation, because this summation stuff I can express this in terms of linear algebra operations. So this whole thing will become a matrix. This guy here, it will become a matrix called the mass matrix for reasons I'll get into later when we get into the physical realm or the physical explanation of all of this. But it's called traditionally the mass matrix, and I have these two phi's are multiplying each other, and they make up a matrix. And I'll get to how this works in detail later, and also in the next lecture I'll get into details of how this works. So this thing is of course a matrix, and it's multiplying our ui. So if you look at these operations now, I is summed in here. So this thing here, this guy is the same as this in here. It's the same operation. I just have extracted ui from this. And of course now I have an equation system, right? Because I can solve for u by just taking this linear system and solve it using, well, you've maybe done it by hand, and you just do you invert this and multiply it with f. But there's much better methods of doing this, and I'll get into that later as well. But this is the math we're going to use now to solve for the nodal solutions in a systematic way. So we can solve for all nodal solutions ui in a systematic way so that we avoid this thing. So we will get the best average. So we will get the best solution by finding our nodal solution. So basically what we have said here is we have 1, 2 elements, and that means we have 1, 2, 3 nodal solutions that we need to find. And this way of doing it will give us the best approximation, the best way of doing this, so, such that we minimize the average error, we minimize the integral between these curves. And there is no better way of doing this on average than this. This is also called sometimes the L2 projection. Either way, this has many meanings. If you dive into computational or numerical analysis, you will get into the details of this, but that's a completely different course. All right, so of course we have to talk about this stuff because the finite element method is a numeric method. It has to do a lot with numerical methods, and when you get into numerical methods, they are numerical because we do them in a computer, so we have to do a little bit of computer programming, otherwise we cannot talk about these issues if we don't program a little bit. And we can do things by hand, but it's not really made for doing things by hand, so we'll get into very complex computations, which of course cannot be done by hand. They're infeasible to do by hand. Now, we want to implement this in MATLAB for our function here. So I'm gonna throw this stuff in here. We want to implement this in MATLAB for the function UE in the range of a to b. And we set, in this example, we set A to 0 and B to 1, so we get our well-known example here. Okay, so I'm just gonna again continue by copying pasting stuff. We set A to 0 and B to 1, and we let the capital N denote the number of subdomains or elements. So this is element 1 and this is going to be element 2. And we're just going to run with 4. So essentially, again, just to make this very clear, essentially we split the range A to B into n subdomains using n number of elements. And this means that we will get n plus 1 nodes. So for 2 elements we have 1, 2, 3 nodes. So always n plus 1 corresponding linearly spaced points between A and B. They really don't need to be linearly spaced, but let's not get into that, because that's called adaptivity, and we're sort of looking at where the error is high and we're throwing in more elements or nodes there. But for just to keep things simple, we just do it linearly spaced. So the distance between the nodes is going to be the same everywhere. We're saying that X nodes are going to be linearly spaced from A to B using n plus 1 nodes. And if I run this, I'll get the following. So I have 5 nodes linearly spaced, so I have a quarter of unit here. Now, it's always nice to visualize stuff. So do it on pen and paper, do it in MATLAB. I'm going to show you how to do this in MATLAB, but there's a lot of things to learn here. So I don't expect you to remember all of this, but you can see me doing it at least, and you just copy the stuff. But please do it on paper, just for your own sake, just to get grasp of this. So I'm doing a figure, I'm doing a plot, so I'm plotting all of these points in zeros, so I'm just multiplying it by 0. I'm stating that the marker should be circles and they should be blue. I'm doing hold on because I want to do other stuff on this thing. I'm creating a grid, or I'm just turning the grid on. I'm moving the axis slightly. I'm putting a padding here, so this thing starts from minus 0.1 and goes to 1.1, so that these points don't just lie on the x-axis here, or this grid here. And then I'm going to throw in a text. So I'm doing 1, 2, 3, 4, 5, and well, without going into details, this is how you do that. I don't want to spend too much time explaining how all of this code works, because I just expect you to copy paste it. And if you have any questions now, I'll gladly answer it, but let's keep this video to a reasonable time format. What am I doing now? So I'm going to create a structured matrix. So these are my nodes, but what I want to create is also a connectivity. So I wanna say that, all right, element 1 is consisting of nodes 1 and 2. Element 2 is going to consist of nodes 2 and 3. Element 3 is going to consist of elements or nodes 3 and 4. On element 5, or element 4, sorry, for those who keep track, is going to consist of nodes 4 and 5. So this structure I'm after is going to look like this. It's going to be a matrix, because I have 2 nodes in each row. So for each element, so the rows are indicating the elements, and the columns are the actual nodes. So if this was a quadratic problem, then I would need to modify this in order to have a middle node as well. So I would have 1, 2, 3 for every element. Okay, I'll get into that later. But for this linear thing, this is how it looks like. And now that we see how this works, first we work this out on paper like this, right? Well, paper, screen, whatever. And then we try to find a general format. So we write out what we want, and we find the general format, and we realize that, okay, we're going from 1, 2, 3 until n, and here we're going from 2, 3 until n plus 1. And then we can recreate this in MATLAB code. So traditionally, this variable is called nodes. I got this from my professor. I'd never bothered to change this to something else, but in different textbooks, you will of course see different notations. I'm just going to use what I'm used to. So these are called nodes, but sometimes I also use elements, because they're really defining the element connectivity. All right, so this is where this leads to. If I run this, I will get exactly what I want. For element number 1, so that's the first row, I get 1, 2, so that's my node 1 and 2. and for the second element I have 2, 3, and then 3, 4, and 4, 5. And you will see how this is used in a second. For now, I'm going to copy the number of nodes given by n node, which is just the length of this vector here. So this thing is 1 times 5, so n node is going to return the number 5. So if I hover over this, I can see clearly that it's 5. Okay. Now, just to get, I understand you have different backgrounds. Many of you haven't seen programming or used programming before, but now you will get the time to get your fingers wet, because we're going to do for loops. So if we're going to, for instance, in this case, we're just going to take it easy and plot a line between the nodes in different colors, and we're going to plot a text for each element indicating E1, E2, and E3 all the way to E4 here. And if you're doing an operation where you know ahead of time that you're going to need to do it 4 times, 5 times, 20 million times, whatever number of times, then you can loop it using a for loop. So that means that you're stating how many times you're gonna do a certain operation, and then you're going to write code in between these for or while or whatever you have, indicating that this code is going to be run these many times. So we are going to do it this way. We are looping over n elements. Everything between the 4 and n will be run n times. Alright, I'm not going to tell you more about this. If you need to know this, then you can check out some help files or video or line or whatever telling you how for loops work, but basically this is it. For IEL 1 to n, that means we're going to run this n times, and IEL is going to be our control variable, well, basically the thing that is going to be incremented. And because this is going to be 1, 2, 3, 4, then we can use it inside nodes here to grab the IELth node, and the colon here means grab everything, all the columns. So we will look at the output. So we can run this. We can see what happens here. Really, I can just also output IEL in here to really see what's happening. So if we can scroll up here, we can see that, alright, so IEL is equal to 1, and then inodes is 1, 2, so that's our first element, the nodes from the first element, and the coordinates are going to be 0 and 0.25, so that's here, this is the first node. And then I'm sort of saying that, alright, so the first bound, the leftmost bound, x1 is going to be whatever it says here for the first element, which is 0, and then the other one is going to be, x2 is going to be 0.25. Going to do the following with it. I'm going to plot x1, x2. So this point here, so this is these are the x components. If you just do plot and press F1 or right click and do help, you can see this overlay. So we're plotting our x coordinates and y coordinates. So this is going to draw a straight line here. This is what this is indicating. It's just a line and a line between x1 0 and x2 0. So just a straight line here. Text, well, it's going to take the mean value from xc here, which is the mean. So in this case, it's the mean between 0 and 0.5, so that's 0.125. This point here, and at this height 0.1, so that's the y coordinate, it's always going to be 0.1, so that's up here. And it's going to insert this text e underscore and then num to string, so it's taking the number IEL, the element number, and converting it back to a string, and then just putting it as a subscript here, so E1, E2, E3, E4. So this is what we're doing with this for loop. I suggest studying it. If you have any questions how this works, then please do a Google search for it, and if you need me to explain any of these, just ask and I will explain that to you. Okay, so now the first loop is, of course, this thing that we're doing here, just to visualize the stuff and get a little bit familiar with it. The others that we're going to do is, of course, going to solve our problem for us. It's going to do the assembly bit. I'm getting ahead of myself again. I'm going to talk about that later. But we have basically 1 degree of freedom per node. So we have one unknown per node. So this u that we are trying to find in order to fit this exact solution, that's a degree of freedom. So inside of these nodes, on these lines, we're trying to find u1, and then here we're trying to find u2, and here we're trying to find u3, u4, and u5. So we're trying to find all of these u1, u2, u3, u3, u4, u5, and they have 1 degree of freedom. They can only move in one axis, so to speak. So that's our degrees of freedom. And the number of equations that are tied to these degrees of freedom is going to be the following. That's what we call number equations, which is the number of nodes times 1, because every node, every unknown, has 1 degree of freedom. In this case, in 1D, that's always true, but in 2D, we have, of course, 2 degrees of freedom, and in 3D, we have 3 degrees of freedom. We can even have other types of degrees of freedom even in 1D. We can have rotation, for instance. We have different problems. So we need to state how many degrees of freedom we have per node. So in this problem, we have 1. Okay, now we're going into the part with the numerical methods, numerical science. We need to pre-allocate stuff. That is for performance sake, because we need to talk about performance. Otherwise, it's going to be this big elephant in the room and nobody's addressing it. All operations take time. When you're using solve, it will take time. If you're using a method by hand, it will take time. And when we're problem solving in general, all operations take time, and the one thing we're after is to minimize computational time. And then once we have done that, we want to minimize engineering time. But basically, time is money, right? And we need to minimize it. Otherwise, when an engineer is waiting for results, that coffee break is going to cost a lot, because that's money we can be spending on actual other type of problem solving. So we need methods that work fast, accurate and fast. And now we're talking about the methods in general, like how do they work, what is the accuracy and such, but we need to talk a little bit about performance. The real science of performance is, of course, outside of this scope. Those engineers are computer scientists. It's a different field from ours. They're focusing on complexity analysis, which is analysis of an algorithmic complexity. Basically, that means how can you minimize, if you want to do a certain type of operations like we're doing. All of this is closed form solutions, so that means that we have an exact amount of mathematical operations that will yield the exact solution. And if you spend more time on it, more operations on it, is just wasting time, because there is a theoretical limit to how many mathematical operations you need to do to get the exact answer. Other problems, specifically iterative problems, and especially problems which have variables that are stochastic, that means probabilities, statistics, that kind of stuff, can have various types of mathematical operations, and the answer will always be a little bit different from the last time you have run it. But on average, the results will be the same for those types of operations. So again, those people who are looking into how complex one algorithm is over the other, those are computational or computer scientists. But we are sort of in-betweeners. Mechanical engineering is is flirting with the field of computational engineering, and then you have, of course, computational engineering as a science per se, and those guys are only looking at how to do computations using the computer. But yeah, so we need to understand a little bit of all these fields, and one of these means that we need to, when we're creating these types of scripts, we need to pre-allocate stuff, otherwise shit will take a lot of time, and we don't have that. We don't have that time. And of course, now I'm not saying that this is the best method of doing it. In fact, this is a very slow method of doing it. We're wasting lots of memory when we're doing it. But again, I'm going into details here which you don't need to know about. Let's just say there's so many methods we can utilize here to make this be quicker. But I'm just talking about stuff that is very basic here. Okay, this is what we want to create. We want to create a mass matrix, or this M matrix, which consists of number of equations, which in our case is 1, 2, 3, 4, 5. So 5 times 5. We want to create a 0 matrix with 5 times 5, and that's what this thing will create. In fact, when we run this, there's a 5 times 5 mass matrix. This thing is actually taking memory on the computer, right? And if it doesn't, then when we are trying to put stuff into these positions, then MATLAB is throwing memory around the place, and it takes time to do that. What we're doing here essentially is we're taking a bunch of memory and just saying, okay, this guy here, this box of memory is reserved, and you can just put stuff in it. You don't need to, basically this is like moving from one home to another without actually getting moving boxes. So you're just grabbing random things like, okay, this is a coffee machine, and then suddenly you're running to your new apartment, which might be like 8 kilometers away, and then you're putting it there, and then realizing, oh, now I have to run back and grab this. This thing is actually giving you boxes, and then you move everything with one truck. So it's very efficient. It's not time consuming. I hope you get that analogy. All right, then we have the right hand side, and of course, like, what am I doing? Let's go back to the equation and show you. So I'm pre-allocating. I'm sort of preparing this stuff here. So I'm creating M and F here. That this is what we're going to need in order to do the actual operation, which we'll get to. All right, and when I'm at it, I can also grab the whole equation and put it in here. So now we're going to solve this, or we're going to prepare for the solution. So I'm going to start coding here now. We want to start out by, and then we're going to create everything from scratch here. So we start out by clearing the memory. So our workspace will be completely clear here. That means that there's nothing here since before, and we will recreate everything just to have it very close by. So now our number of element is going to be 4, and then we have our nodes are going to be linearly spaced between 0 and 1, and plus 2. So we will have these nodes here at these coordinates. Okay, now I'm just gonna paste in a bunch of stuff here, like so. So we have our number of nodes, we have the actual nodes, we have our equations and everything. So all of the stuff that we have done before is now here. Just putting a semicolon here, removing the stuff. So for our exact solution, again, I'm gonna copy it in here because I've just deleted all the memory, so we don't have anything dirty there. Now, this is our true solution, and we can plot it. In fact, let's do that. So in a fresh figure, we have this plot. This is our exact solution. Now we're going to create the basis function. So we're taking the general format of the linear basis function, and we're inserting it here, and it's going from A to B in general. So we can access, or we can recreate basis functions for every single subdomain or element that we are in. All right, now the core of any finite element method, the for loop for assembly. So we're doing for IEL, which is the ith element. That's going to 1 to n, the number, and where n is denoting, of course, the number of elements. And the nodes, the inodes, is going to be nodes. We're going to grab it from there, IEL, and then all of them. So let's just run this and see here. So for the first element, we have node 1 and 2, and so on. So this stuff you know about now. Then we grab the x coordinates, xc. So those are all the x coordinates, and of course they are taken from our coordinate vector x nodes, and we are taking the nodes that are corresponding to this element, which is of course inodes. So this is our first element coordinates, and the second element coordinates, and the third element coordinates, and the fourth element coordinates. Okay, nothing special yet. We've done this. Let's just, for, well, readability's sake, call these x1 and x2, so that we don't need to always write xc of 1, otherwise we're going to do that all the time. So we have our coordinates here, x1 and x2. Those are local coordinates for each element. We have different ones. By the way, this stuff that shows up when you do mouse hovering over, it's going to be for the last element. So all of these numbers are for the last element, because this is run now, and then at the end you're seeing the last element. Okay, now we create our phi, which is the basis function for the current element, because it's varying, right? So x1 and x2 is changing, so we're looking at phi here now. So phi is going to be different for each element. Okay, good. Now we can create this mass matrix here, this guy here, which is this integral here. And before we actually do the integral, let's just look at the product of phi times phi, because this is on index notation, and I haven't really shown you how this looks like mathematically. So let's just take a look at that, because I think it's quite important to see that. So I'm gonna create a matrix notation here, and what I want to do is the following. It's going to be 2. So let's do let's do it like this: var phi 1 and var phi 2. So this is of course the transponent of our var phi. So if I do it like this, var phi, and I somehow need to denote, I can't do this bold unfortunately in MATLAB, so I need to sort of denote that this is a vector. So I'm just going to put a vector notation on top of this, and then I'm going to do transpose like so, and I'm going to multiply it with the same over here. So this operation is the same as doing the following. I'm going to grab this, and then this is var phi 1, and I'm copying that over here, and this is var phi 2. So what does this yield? So this is going to yield phi 1. Let's get rid of this. Phi 1 times this, and then phi. If you look at the size of this, this is a what, 2 by 1 matrix. 2. So the inner are the same. That means that this operation is valid and algebraically, and the outers are going to be 2 by 2. So this is going to be 2 by 2 matrix. So let's do that. And the inner is going to be phi 1 times phi 1, or phi 1 times itself, and then we have phi 1 times phi 2 over here. This times this times this. Yeah, so this guy times this, and then var phi 2 times this. So, well, it's the same. Let's just not change the order. And then we have var phi 2 times var phi 2. So this is the matrix we're going to create using this operation. And this stuff here is the same as this internal stuff here, phi j times phi. Just this is on vector notation, and this is on index notation. So the notation are different. And if you haven't done any tensor algebra like that, then this might be this is probably not going to be familiar to you, but this is what it is. Now that we have this mathematical preliminary out of the way, we can take this multiplication in here. So we do phi, but this is a row vector, so we need to transpose that, and we need to be careful how we transpose that, because if we just do the conjugate transpose, then of course we're going to end up with these ugly conjugate numbers here. We don't want that. It doesn't really matter. It's just we know that this is a real number, so we could really get rid of it by saying real here, and that makes the notation a little bit easier, right? So now it's a real number, and of course this bar is away. But if you want to do the exact transpose, then we can put a dot in here. This means transpose, like the standard transpose. This is conjugate transpose. The mathematical operations on real numbers are not going to differ. They're going to be exactly the same. So the results of this and this is going to be exactly the same. I just find this a little bit more cleaner. I don't need to write this dot. So I like this. But then this bar shows up if we don't put this assumption that x and a and b, or really x, is a real number. So I hope you get that. But yeah. We have transposed that and we just multiply it by itself and we get this matrix, right? So this is phi1 times phi1, it's squared, so that's why the square sign, and then here we have phi2 times phi1 and we have phi2 times phi1. So we have this symmetric matrix, and yeah, it's the same stuff as we have seen up here. Good. So now that we see this, we can integrate it. So we do integrate, and we throw this in here and we integrate with respect to x from what? Well, from our lower bound, which is x1, to our upper bound, which is x2. We run that, and this is our matrix. So we have a mass matrix here for every element, 4 of these. Alright, now we call this our mass matrix, and I call it ME to denote that this is an element mass matrix. Now I can get rid of this, just comment it out. It was interesting to see in the beginning how this looks like, but now I don't need to see it. Note, however, and I will get back to this later, that this is a quadratic function. You see that, I hope. Quadratic function. We will not have the time, the computational time to use integration, and I'm saying symbolic integration in finite element method. This costs so much performance to run that. So we will later find tricks how to do this integration, how to get rid of int here, how to just do this numerically. The whole, like half of this whole course of this theory is about just getting rid of this integral sign, because it's very expensive. We want to do this differently. So just note that we are doing stuff very efficient here. But this method is still the same. We're making the small integration in here for every element to create this mass matrix. Okay, I'm gonna leave it in there, and I'm going to do this other integral, which is of course this guy here, the right hand side. So what I want to do is I want to take the exact function which I have here, and I want to multiply this with phi. So I'm doing UE times phi. Right, and also note here that this thing really needs to be transposed. So because this needs to be a column vector, and right now it's a row vector because phi is a row vector. So transposing. And there we go. This is a row vector now. Sorry, again, a column vector. And now we can integrate it. So we do integration with respect to x from x1 to x2. And this is what we call the element load vector, FE. And there we go. We have it here. Right. Now, what do we do with this? Well, these are all tied to these degrees of freedom here, 4 and 5 in this case, in the last element. They need to go in a special place, and I'll get to details about this in the next video. But right now I'm gonna tell you that, alright? So the mass matrix, at these positions here, we're going to insert, we're going to take the stuff that is already there. In the first element, of course, it's just going to be zeros, but then we will actually have stuff in there, and we're going to add ME on top of that, and this is called assembly. So again, you don't need to understand this fully now, we'll get to this later. Just watch me doing this way. F I naught plus FE, like so. And actually, let me get rid of these. I want to show you what the output of this is. So for the first, yeah, I not I'm around, but that's how it is. So for the first element, we are here. So we're putting all of this ME business into this matrix. And of course, this is now a numerical matrix. So the symbolic values are converted into decimal values here, double precision decimal values. So we have ME here, and then the next one is it's going to be here. So if you scroll down here, so it's taking the old value, which is 0.083 something, and it's adding 1/12 to that. So this is of course double the first amount, and so on and so on. And again, I'm gonna get into details of why this is, how this works, and all of that business. But basically it has to do with this averaging. We're sort of averaging stuff in these matrices. Good. Now, this is the assembly business. These are our integrals. We have now finally m and f, and we can solve this system. I'm going to show you what we're doing when we're solving it, because we're basically doing this operation m times u is equal to f. So let's, just for completeness sake, let's create these unknowns so you can see that this will yield a system of equations. So I'm creating u here, and I'm going to create it a little bit different. I'm going to create it u1, 2, and plus 1. So doing it this way, I will have created n, which is equal to 4. So if you look here in the workspace, we have u1, u2, u3, u4, u5, but we also have u. And u, here, lowercase u, is going to be these values. Alright? So, what I want to do with this now is I want to take my mass matrix. I want to do this mathematical operation. I want to take my mass matrix and I want to multiply it with all of these values. Again, let me show you mathematically what I'm doing. I have a 4x4 matrix, so I have this guy here. I have m 1 1 all the way to m 4 1, and I have this. I'm multiplying this with the following: u1, this guy, and this is going to be equal to the following: f1 on down to f4, right? Good. So this is the operation I'm doing, and now I'm taking m and I'm multiplying with u just to show you that this will actually yield this system of equations. So I'm multiplying this by u. I need to transpose that because this is a row vector. So I'm transposing u, and let's see that. Yeah, of course I need to do the proper transpose because otherwise I'll get this conjugate transpose business, and I don't care about that. All right, and this is equal to f. Bam. This is our. All right. So f is of course containing a bunch of stuff, which is, I mean, the fraction is horrible. So let's just do VPA on this just to show you this a little bit more manageable. Let's like do 2 of these, so maybe it looks, yeah, good. Okay. So this is our equation system. So we can sort of say that, all right, this is x like that. So these are equations, and we have 1, 2, 3, 4, 5 equations, and we have 1, 2, 3, 4, 5 unknowns. So the system is solvable. So we can, using the same way, I'm just going to do s here, we can throw this into solve EQS and just get our solutions, because s will now contain our solutions here. So we can sort of, this is a slightly different way of accessing the solutions, but you see the solutions here. And I'm not going to use these. I just want to show you this is one way of doing it. But now let's look at the time it takes to run this. So we can put tick in front of a operation and talk afterwards, and we can see it sort of starts a timer at tick and it ends that timer at talk, and it's going to display the time it took to run this. And of course we will do it here as well to see how long our symbolic operation takes for solving this, right? And now let me show you how to do this numerically. I'm going to time this as well. So the numerical solution for this is just by doing the following: u is equal to m backslash f, and these are solutions. Please note the time difference. This is the time it takes to solve this thing symbolically using solve, and this is the time it takes to solve this numerically using the backslash operator, which is the same thing as lin solve, which is a set of of linear algebraic methods, where the Gaussian elimination method is one of them, but there's of course many more. You can do F1 on this, and you can see what it does, and you can also read lots of business about what actually what algorithm it uses to solve this thing. So yeah, there's that. Also, it's a closed form solution, so it's not iterative. It's not a conjugate gradient method or anything like that. Anyhow, it's much faster, much more efficient than to use anything that is symbolic like this. Also, please note how long it takes to assemble this stuff compared to actually solving. It's like 4 times longer, and this will just increase with the number of elements we have. So timing is important. We want to use the method that is most efficient in terms of performance and accuracy, and this is it. All right, so let's plot this. So we have our true solution here, so you can just hold our plot and add on top of that. So the thing we're going to add is a standard plot. Let's bring up the help on that. So x and y. So our x coordinates are just x node, and our y coordinates are of course our u values, and we are going to connect these with lines. So we're just going to put this here, and we're going to put markers, which are circles, and we want to have them colored blue. So this will yield our actual solution like this. So note that these are now connected. There's no discrepancy here like we had in our first example up here, and they're sort of minimizing the area between these curves. And there's also the dots are not on the red lines as well, so this is on average the best fit. Now we can really play around with this nicely. We can go in here, we can increase this, we can double this. Let's actually put it to 10 and see what happens. So we're running this with 10 elements, and this is what we get. So we get a really nice or nicer solution. Also note how long it takes to actually solve this equation system, 0.04 compared to 0.20. So this is quite much faster, and the actual assembly is taking horribly long time, 4 seconds, almost 5 seconds to actually assemble this, and most of this time, if not all, is spent on these two integrals here. This is horribly inefficient, and we cannot use this method here. I mean, really, this is like really inefficient. So that's why the rest of the course pretty much is going to be all about how to get away from integrating symbolically. Good. Now, this is it. This is what piecewise approximation is all about. We're doing piecewise linear. These are lines approximations. Our phi, which we have chosen, is a linear function. Of course, you can replace all of this with quadratic approximation. In fact, you will do. One of your exercises is going to do this quadratically, but you have to wait for the next video. Watch that first before actually getting into this. This is sort of a preview of what you will be doing soon enough. Now, I want to get this concept out of the way, that when we are increasing the number of elements, the error goes down. Now the question is, how much does the error go down? That's one question. The other question is, how the hell are we computing the error now? Because earlier it was just easy to just integrate the difference. What is the difference here now? This is pointwise. How do you do that? Well, we have to do it by element again. So we have to watch what the difference is for each element. So let's do that. We are going to call that the L2 error. Well, it's really called the L2 error. We don't have a choice. This is what it's called, the L2 error. And this is how you do that sort of piecewise. So we're summing for every element, and we're computing for every element. We are computing the integral between these two curves. So we have our approximation and we have our true curve, and we're, well, basically squaring that, and we're integrating in that square. And then we're summing all of these for every element, and at the end we're just taking the square root out of that sum. That's the definition, and I should really put this as a definition for the L2 error. Alright, so in code, this is, well, we can start with the L2 error and set it to 0, and then do for IL is equal to 1 to n. We're going to do a bunch of things. So the first things we're going to do are just the same, so we're just going to copy these because we need the coordinates. So we copy that in here, so now we have the coordinates for every element, and we also need the actual phi, the basis functions. So we're going to copy that as well. And now we can grab our u. So we're going to call it ui. So the I stands for the ith element, so for every element. So we have u, and then just going to grab I nodes, and this works the same way as x node. So these are coordinates, and these are u is our corresponding nodal values. So ui here, if you just grab that, run this, then ui is just our nodal values for that particular element. And now, as you did earlier with just one element, you can create the linear function by taking phi and multiplying that with the nodal coordinates. So now we have an approximate solution here for every element. Okay, so once we have that, we can take the difference. We can do ui minus ue, and we need to square that. So we're squaring it and we're integrating it. So we're doing integration of this difference squared, this squared difference, with respect to x from x1 to x2. So this integral is going to be dumped into the L2 error. So L2 error is equal to previous L2 error from the previous element, if I can spell that right, plus this integration business. Run that, and let's see what we have. L2 error is undefined, and I'm using the wrong variable. And this probably looks horrific. Yeah, indeed it does. So we can convert this to a double like that, just to be able to view. Wow, MATLAB decided to be really slow on me now. So I just want to see a simple L2 error. Where is it? There we go. Yeah, so I'm seeing this accumulated L2 error now. Alright, now let's get rid of this other business here. It's horrific, we don't want to see it. And once we have summed everything, we just say L2 error is equal to L2 error, and actually the square root of that, sqrt. So we're squaring that. So the sum, this is a sum, is going being squared, and this is the solution of that thing at the very end. So our L2 error for 10 elements is 0.0150. This doesn't tell you much now, but what we want to do with this is actually a convergence analysis. Convergence analysis. Convergence analysis. Alright, so what we're doing? Well, let's do it for a couple of, let's say like 2, 4, 18, 16, 32. Yeah, that'll be fine. So I'm gonna do that as a matrix perhaps. I need what? 1, 2, 3, 4, 5, 6. So the 6 by 2. 1, 2, 3, 4, 5, 6. So I'm gonna put the number of elements here and the L2 error here. Alright, and starting with 2. So 2 elements. I'm gonna go back and do 2 elements, and let me actually get rid of yeah, this. So it's just one section with the whole solution business. So I set n to 2 and I run this, and I get this very coarse solution here, right? And this is my L2 error, so I'm just gonna copy that thing. Can I do that somehow? No. Well, type it in here. That's 0.4745. Okay, and I'm gonna do it now for n is equal to 4. Same stuff. And I will get an output at the very end there. So n4 is equal to 0.1106. And I'll continue with 8, and I'm just doubling the number of elements here, 16, and at the end 32. I'm gonna fill this in, which becomes for 4 and for 8, and I suggest you run this 0.0239, and then for 16 elements we have 0.0057, and finally for 32 we have 0.0014. Okay, so we're sort of seeing that we're sort of, when we are increasing, when we're doubling the number of elements, we're getting sort of 1/4 of the error. That's quite interesting. So let's see this graphically. So what we have here is n equals to, and I'm just going to copy all of this stuff. So this is n, and our L2 error is going to be this error thing, like so. Just copy that in there, and I'm going to do a figure, and I can do a plot of this. So I can do, alright, so the x-axis is going to be n, and the y-axis is going to be this error, and I want this to be connected by straight lines with these marker signs, and I can see this sort of like shrinking down to nothing. Alright, so this plot obviously is not telling us anything. Let's do logarithmic. So we can change the x-axis here to a logarithmic axis and the y-axis to logarithmic, but there's a faster way of getting there. It's just to do a log-log plot. This thing is called log-log, so it's a function called log-log scale plot. So both scales are going to be logarithmic. Now if I run this, I will get the straight line in this logarithmic plot. And if I now find out the slope inside of this log-log plot, I know which convergence rate I'm having. So what I want to do is first I want to, well, I did this in Swedish, so I apologize. I'm going to change this to convergence analysis, like so. So I have a grid, I have number of elements here increasing, so I'm doubling it every time, and my error is like shrinking down to nothing with a certain convergence order, and I want to find that rate. And I put it to you that this rate is given by the difference by the delta of the log L2 error over delta of log n error. So basically the slope, right? So let's do that with MATLAB. So if you do diff on a number, on a what's it called? On discrete values on a vector, you're just going to get the difference, like one value minus the other value. So it's not, has nothing with differentiation to do when it comes to vectors. And this dot divided by means I'm doing it for every element. So every element in this vector here, I'm dividing by this, every element in this vector here. So it's a point-wise or element-wise operation I'm doing. And this is my rate. It's negative, sloping downwards, with around 2. So that means that this is a quadratic convergence or second order convergence. And we can clearly see that. And we also have an explanation that for every doubling of the number of elements, we get a decrease of the error, which is 4 times. So 4 times decreasing. Yeah, and you know, you can do this and show this theoretically that this is true, but that's too much mathematics, so I'm not gonna do that for you here. That's way above your pay grade. So let's just keep it sort of basic. I mean, we're sort of dived into stuff here, but this is the deepest river or deepest lake that we are going to dive to. We're not going to do stuff that is more deeper than this analysis here. Of course, just remember, this seems like a lot, but we're just scratching the surface of knowledge here. There's so much stuff you can learn about computation and finite element method and everything. This is the sort of mathematical mathematical depth of it, and later when we dive into SolidWorks we will go into the depth of the actual computations of how you set up your model, how you do the practical stuff. There's a lot of depth there as well, but what we have seen now is that this is the finite element method. When you do stuff in SolidWorks, that's called finite element analysis, where you're using this theory applied on a physical problem to solve an engineering problem. So those are basically two different fields, but when you want to know about the finite element method, which this course is partly about, then you need to understand the Galerkin method and how you add these elements up to get a nice solution. And again, we're doing it very basically here. We're not approximating a differential equation, we're just approximating a function, but in the next session we will actually learn how to do this for differential equations, and that is really helpful. Alright, so much more stuff to do. I suggest you practice this by changing out, and I will give you an exercise to do that in a work package, where you will fiddle around with this a lot. So please understand this stuff, because this is the first building block of understanding everything that has to do with how this works. And your implementation will be at the very end, and this is going to be part of the examination. There's going to be an examination problem where you're supposed to solve and create a full finite element solver in one dimension. So this is the first block of understanding that. Alright, study hard, and I will see you in the next video. Goodbye.